Have you ever wondered what happens when a star suddenly starts acting strangely? Betelgeuse, the massive red supergiant in Orion, dimmed dramatically in 2019, baffling astronomers around the world. What caused this cosmic giant to flicker and fade, and what does it reveal about the life of dying stars? Let's dive into this mystery together, and if you enjoy exploring the universe, don't forget to like and subscribe for more amazing space stories. In the familiar winter skies of Earth's northern hemisphere, the constellation Orion stands out like an ancient celestial warrior, recognizable to nearly every culture that has ever looked up in wonder. At the shoulder of this great figure glows Betelgeuse, a fiery red beacon that has captivated astronomers, storytellers, and casual skywatchers alike for centuries. It is normally one of the brightest stars in the night sky, massive, imposing, and visibly tinted with a warm reddish hue even to the naked eye. For as long as humanity has observed it, Betelgeuse has maintained a relatively steady presence, bright enough to act as a cosmic landmark that anchors our sense of the winter heavens. Because of this consistency, anything unusual about its brightness is immediately noticeable, even without scientific instruments. So when Betelgeuse suddenly began to fade in late 2019, dropping to a fraction of its usual brilliance, the effect was striking. The star that had defined one of the most iconic constellations appeared to be fading away before our eyes. The unexpected dimming of Betelgeuse created an immediate mystery. This wasn't the gentle, rhythmic fluctuation typical of red supergiant stars known to swell, cool, and brighten in cycles lasting months. Instead, Betelgeuse's drop in brightness happened quickly and dramatically, shifting from its usual place as the 10th brightest star in the sky to barely making the top 30. Whole communities of backyard observers noticed the change by simply glancing upward, while professional astronomers began receiving a flood of reports that something unprecedented was happening. It wasn't long before the excitement spread worldwide. Why was this ancient giant dimming so rapidly, and what did it mean? Had we just witnessed the first signs of a star about to go supernova, a catastrophe so immense it would momentarily outshine the moon? Astronomers were genuinely shocked because such dramatic changes in a red supergiant of Betelgeuse's scale are rare on human timescales. These stars live fast and die young, evolving over millions rather than billions of years. But even within that turbulent lifespan, major changes are still slow compared to a human lifetime. The dimming was not something expected in any of the established models of red supergiant behavior, which made the event all the more extraordinary. Some researchers compared it to witnessing a volcano that had slumbered for thousands of years suddenly show signs of awakening. Others described it as a cosmic alarm bell, an event so rare that astronomers might only witness it once in their careers, if ever. The shock of the dimming wasn't simply that Betelgeuse changed, but that it changed so much, so quickly, and in a way that could signal a profound shift in the star's evolutionary path. In those early months, the night sky felt different. The shoulder of Orion was no longer the steady red ember it had always been. It had become a flickering, uncertain light, as though something immense and hidden was stirring within it. For astronomers watching from observatories around the world, the event felt like opening a door into the private life of a dying star, an opportunity to catch Betelgeuse in the middle of doing something no one had ever seen before. It was this combination of mystery, rarity, and the potential for witnessing the prelude to a supernova that made the dimming of Betelgeuse one of the most captivating astronomical events of the century. Betelgeuse is not just another star in the sky, it is one of the most extraordinary and extreme objects visible to the naked eye, a cosmic titan living in a brief and turbulent stage of stellar evolution. Classified as a red supergiant, Betelgeuse represents one of the final phases in the life of a massive star. To understand why it behaves so strangely, you first have to appreciate the sheer scale and nature of what Betelgeuse actually is. If placed at the center of our solar system, Betelgeuse would extend far beyond the orbit of Mars, possibly enveloping Jupiter. It is roughly 700-1,000 times the diameter of the Sun, and its surface is so distended and diffuse that it borders on being more like a cosmic cloud than a solid sphere. With a luminosity tens of thousands of times greater than the Sun's, Betelgeuse burns through its nuclear fuel with astonishing speed, living fast and dying young. While our Sun is around 4.6 billion years old and still in its stable phase, Betelgeuse is estimated to be only 8 to 10 million years old, an infant in cosmic terms, yet it is already in the final chapters of its life. It was born as a massive hot blue star, lived for only a fraction of the Sun's lifespan, and is now swollen into its present bloated, unstable form, signaling that its internal nuclear processes are approaching collapse. In this red supergiant stage, Betelgeuse behaves in ways that are both fascinating and chaotic. Red supergiants are known for their regular pulsations, slow breaths that cause the star to rhythmically expand and contract. These pulsations occur because the star's outer layers are loosely bound and respond dramatically to changes in internal pressure and temperature. During one part of the cycle, the outer layers heat up, expand, and cool, causing the star's brightness to decrease. Later, gravity pulls these layers back inward, compressing and heating them, which raises the brightness again. For Betelgeuse, these cycles traditionally occur over periods of around 400 days, though modern research shows it may have multiple overlapping cycles with different timescales. These pulsations are normal for stars of its kind. They are signs of a massive, aging object trying to maintain balance as nuclear fusion in its core transitions through increasingly complex stages. But even by red supergiant standards, Betelgeuse is unusually active. Its surface behaves like a restless sea of giant convection cells, some of which may be as large as the distance between the Earth and Mars, rising, cooling, and collapsing in unpredictable patterns. These processes influence temperature, brightness, and overall stability. What makes Betelgeuse particularly unstable, even among red supergiants, is its evolutionary stage. Stars like Betelgeuse fuse hydrogen for only a brief portion of their lives before swiftly progressing to helium, carbon, neon, and heavier elements in their cores. Each stage becomes progressively shorter, and each creates new layers of internal instability. Betelgeuse is at a point where its core is no longer dominated by hydrogen fusion, and its internal structure more closely resembles an onion, multiple layers where different elements undergo fusion at different rates. This complicated layering creates turbulence, irregular pressure waves, and violent convective motions. The outer atmosphere, a vast envelope of gas so thin that it resembles a vacuum compared to Earth's atmosphere, responds dramatically to any internal shift. As it nears the final stages before a supernova, the star sheds mass in enormous quantities, creating dense, chaotic shells and arcs of gas that surround it. This mass loss is not smooth or continuous. It happens in eruptions, giant plumes, and sudden expulsions that destabilize the star's appearance from Earth. Because Betelgeuse is in such a rapidly advancing phase of its evolution, it is expected to exhibit signs of instability, mass loss events, irregular pulsations, fluctuations in temperature, and surface disturbances far larger than anything that occurs on smaller stars. But even with these expectations, Betelgeuse stands out. The combination of its enormous size, its advanced stage of burning heavier elements, and its extremely complex convective processes makes it one of the most variable and unpredictable red supergiants ever studied. The star's surface, if it can be called that, is constantly in motion. Giant bubbles rise and fall, shock waves ripple outward, and the tenuous outer layers are always at risk of being pushed off into space. This rapid internal and external evolution is precisely why astronomers pay such close attention. Betelgeuse is living through a stage of stellar evolution that humanity rarely has the privilege to observe in real time, and every strange change, dimming, brightening, pulsing, or eruption is a clue to understanding how massive stars die. Its instability isn't just a quirk. It's a sign that the star is nearing one of the most dramatic endings a star can have, one that will shape the future of its region of the galaxy long after its final light has faded. The 2019-2020 Great Dimming of Betelgeuse remains one of the most dramatic, puzzling, and scientifically valuable stellar events ever witnessed in real time. Before the dimming began, Betelgeuse had spent centuries shining as a reliable, reddish-orange beacon in the shoulder of Orion. Its variability was known, but predictable gradual brightness cycles that astronomers had charted for decades. Yet toward the end of 2019, something began to unfold that broke every expectation. The first unusual hints appeared in late October and early November, when professional observers noticed that Betelgeuse was slipping below its expected luminosity curve. At first, the decline seemed modest, something that might fit into the natural rhythm of the star's overlapping pulsation cycles. But within just a few weeks, the drop accelerated more rapidly than any models predicted. By early December, its brightness had dipped nearly 30%. For a star as famous and easily visible as Betelgeuse, this change was obvious even to casual skywatchers. What followed in January and February 2020 stunned the astronomy community. Betelgeuse kept fading. By mid-February, it had dimmed by almost 60%, becoming the faintest it had ever been in recorded history. The proud red shoulder of Orion, usually among the most striking features of the winter sky, looked strangely muted, as though part of the constellation had been drained of its fire. The sudden drop in brightness triggered an immediate wave of global curiosity and concern. As the dimming intensified, public interest exploded across social media, news outlets, and scientific forums. Betelgeuse has long been known as a potential supernova candidate. Its massive size and late evolutionary stage make it destined to explode in cosmic fireworks at some point within the next 100,000 years. To the general public, a century or millennia may seem distant, but astronomers know that when a star is nearing the end of its life, its behavior can appear chaotic and unpredictable. So when Betelgeuse suddenly dimmed at an unprecedented rate, people began asking a remarkable question. Was this the moment? Was Betelgeuse preparing to go supernova before our very eyes? The possibility, while unlikely, was not dismissed outright. Scientists explain that although a dimming itself doesn't guarantee an imminent explosion, major instability in a red supergiant could, in principle, signal internal turmoil preceding core collapse. Headlines erupted worldwide, speculating about whether humanity was about to witness one of the most spectacular events in the modern history of astronomy. A supernova from Betelgeuse would briefly shine as bright as a crescent moon, be visible in daylight, and reshape our understanding of dying stars. The idea of such an event occurring in our lifetime sent both excitement and fear rippling across the globe. As the world stared upward, scientists rushed to gather as much data as possible using every instrument capable of studying Betelgeuse's behavior. This became an international, multi-wavelength effort involving ground-based and space-based observatories alike. Optical telescopes tracked the star's changing brightness with exquisite precision, while infrared telescopes such as the Very Large Telescope, VLT in Chile, examined Betelgeuse's surface structure and temperature variations. Interferometers, specialized instruments that combine light from multiple telescopes, provided unprecedented high-resolution images, revealing that part of the star's disk appeared darker and more distorted than usual. The Hubble Space Telescope added a critical piece of the puzzle, observing Betelgeuse in ultraviolet wavelengths, which allowed astronomers to detect signs of heated, outflowing material in its outer layers, evidence that something powerful and unusual had occurred just months before the dimming began. Radio telescopes monitored mass loss and gas movement in the star's extended atmosphere, while amateur astronomers worldwide formed an essential network of observers, continuously recording data through the months-long event. Their combined efforts allowed researchers to create a detailed timeline, capturing changes in brightness, shape, temperature, and surrounding dust. The 2019-2020 Great Dimming was not a single moment but a rapidly unfolding sequence of changes observed live with a richness of data no previous generation could have imagined. The event brought nearly every major astronomical facility into collaboration, highlighting how even familiar stars can surprise us in profound ways. While Betelgeuse eventually began to brighten again, returning toward its normal luminosity by late spring of 2020, the mystery of what caused the dimming reshaped our understanding of massive stars and opened new avenues of research into the final stages of stellar evolution. More importantly, it showed the world that the sky above is not fixed or static. It is alive with change, drama, and events unfolding on scales far beyond our imagination. The Great Dimming became not only an astronomical event, but a reminder of humanity's shared curiosity, the instinct to look upward, to question, and to seek answers when the universe behaves in ways we do not expect. A surface mass ejection from a star like Betelgeuse is an event so extreme that nothing in our own solar system truly compares to it, not even the most powerful outbursts our sun has ever produced. Our sun regularly experiences coronal mass ejections, CMEs, where magnetically charged plasma erupts from the corona and streams into space. These solar events are impressive on a human scale, capable of disrupting satellites and power grids, yet they are tiny flickers compared to what happened on Betelgeuse. A surface mass ejection, SME, is vastly more violent. Instead of just the corona, the sun's thin outer atmosphere, being expelled, an SME involves the ejection of large portions of a star's photosphere, the star's actual visible surface. Think of it as if the sun suddenly tore away a chunk of its outer skin, hurling it into space with unimaginable force. Betelgeuse's SME was the first time astronomers had ever directly observed such an event from a star beyond the Sunday. It was like witnessing a volcano erupting on a scale so huge that even light itself struggled to escape from behind the debris. The amount of material Betelgeuse expelled during this event was staggering. Observations and modeling suggest that the star launched several times the mass of the Moon into space in a single violent outburst. To put that in perspective, if the Sun produced an equivalent event, it would eject hundreds of thousands of times more material than it does in a typical coronal mass ejection. This wasn't a small, gentle puff of stellar wind. It was a colossal eruption driven by intense convective forces deep within the star, and likely triggered by the sudden rise of an enormous, hot bubble of plasma. This bubble surged to the surface, destabilized a portion of the star's photosphere, and blasted it outward at tremendous speed. As this material rushed away from the star, it cooled dramatically. In the weeks that followed, the ejected gas condensed into a dense cloud of dust, a cloud large enough to partially obscure Betelgeuse from our vantage point on Earth. This dusty veil became the key ingredient behind the Great Dimming, casting a shadow across our line of sight. The outburst did not merely throw material outward, it disrupted Betelgeuse's entire outer structure, setting off a chain reaction of turbulence and recovery that lasted months. When such a large section of the photosphere is violently removed, the star has to physically restructure itself. Betelgeuse's surface behaved like a disturbed ocean giant. Waves of gas sloshed, convective cells reorganized, and temperature gradients shifted unpredictably. Regions of the star cooled dramatically, forming massive dark patches, starspots far larger than anything seen on the Sunday. These cooler regions further contributed to Betelgeuse's dim appearance, compounding the effect of the dust cloud outside it. Meanwhile, shock waves rippled through the outer layers, temporarily altering the star's normal pulsation cycles. In essence, the surface mass ejection punched a temporary but enormous hole in the star's equilibrium, causing Betelgeuse to dim not only because of the ejected dust blocking our view, but also because the star itself was recovering from a traumatic upheaval. This event forced astronomers to reconsider what red supergiants are capable of. Before the 2019-2020 dimming, no one had confirmed that stars could experience surface mass ejections on this scale. Betelgeuse showed that its outer layers are far more unstable, more dynamic, and more violently active than previously imagined. The SME wasn't just a dramatic episode, it was a revelation about the messy, explosive final stages of a massive star's life. It became clear that Betelgeuse is shedding enormous amounts of mass as it inches closer to its eventual supernova, and that these eruptions may be far more common, powerful, and influential than anyone realized. The shock of the event wasn't only that Betelgeuse dimmed, it was that the star demonstrated a kind of eruption that astronomers had never seen before, rewriting the understanding of how massive stars behave on the brink of collapse. When Betelgeuse expelled that enormous mass of hot plasma during its surface mass ejection, the material did not simply disperse harmlessly into space. Instead, the ejected gas underwent a dramatic transformation as it traveled outward from the star. Immediately after leaving the surface, the plasma was blisteringly hot, millions of degrees composed of ionized atoms and energetic particles. But as it expanded into the vast emptiness surrounding the star, it began to cool rapidly. In the outer regions of Betelgeuse's atmosphere, temperatures dropped significantly, and as the ejected material decelerated and spread out, it passed through a range of conditions that allowed something remarkable to happen: dust formation. Small molecules began to condense out of the cooling gas, the same way steam in Earth's atmosphere condenses into droplets that form clouds. Except here, the droplets were not water, they were microscopic grains of silicates, carbon compounds, and other mineral-like particles. These tiny grains clustered together, growing denser and forming a thick, expanding shroud around the star. Within weeks, what had started as a violent burst of incandescent plasma became a cool, opaque cloud drifting across Betelgeuse's outer environment. The formation of dust around a red supergiant is not unheard of. These stars constantly lose matter into space, building shells and arcs of dusty material over centuries. But the scale and location of the dust created by Betelgeuse's 2019 outburst were unlike anything seen before. This dust cloud happened right along our line of sight, positioned almost perfectly between Earth and part of Betelgeuse's visible surface. To understand why this caused the star to dim so drastically, imagine the star as a glowing lantern and the newly formed dust as a thick layer of smoke drifting in front of it. Even though the lantern still burns just as brightly, the smoke blocks some of the light from reaching your eyes. The same principle occurred with Betelgeuse. The dust grains were highly efficient at absorbing and scattering visible light, especially at the wavelengths where Betelgeuse normally shines brightest. Instead of the full radiance of the star reaching Earth, a significant portion of it was intercepted by the dust cloud, turned into heat, and re-radiated at longer, infrared wavelengths that our eyes and even many telescopes do not readily detect. Starspots on red supergiants like Betelgeuse are far more dramatic, far more extreme, and far more influential than the sunspots we are familiar with on our own Sunday. On the Sun, sunspots appear as relatively small, dark patches caused by magnetic activity suppressing convection and lowering the surface temperature. They may be thousands of kilometers across, but compared to the Sun's entire surface, they are tiny speckles. On red supergiants, however, the situation is entirely different. These colossal stars have convective cells so massive that a single one can span the distance between Earth and Mars. When a region of the surface cools due to reduced convection or internal disturbances, the resulting star spot is not a mere blemish. It can engulf a significant portion of the star's entire visible hemisphere. In Betelgeuse's case, its outer layers are so extended and unstable that huge areas can cool simultaneously, forming vast regions of lower temperature that dramatically affect its brightness. Star spots on red supergiants are not only large, they are monumental, shaped by enormous flows of gas rising and sinking in cycles far more powerful and chaotic than anything seen in smaller, stable stars. During the Great Dimming event of 2019-2020, observations showed that an unusually large portion of Betelgeuse's surface was covered by these massive cooler regions. Some estimates suggested that up to 50% or even 60% of the star's visible surface may have been darker and cooler than normal at the peak of the dimming. That means that half of the glowing surface, already a turbulent, roiling ocean of gas, was overlaid with enormous star spots that reduced the amount of light being emitted into space. High-resolution imaging from the Very Large Telescope, VLT, revealed changes in Betelgeuse's surface structure, showing distinctly darker areas that had not been present before the dimming began. These dark patches weren't evenly distributed. They appeared more prominently on the southern half of the stellar disk, giving the star an imbalanced, lopsided appearance. This indicated that the cooling was not uniform but had been triggered by a localized disturbance, possibly connected to the violent surface mass ejection that occurred shortly before the dimming. When the star expelled a massive bubble of material, the structural disruption may have caused convection cells to collapse or reorganize, creating zones where heat failed to rise efficiently from the interior. The effect of these star spots on Betelgeuse's brightness was profound, and they played a crucial role in amplifying the dimming caused by the dust cloud. Star spots are cooler than the surrounding stellar surface, sometimes by hundreds of degrees. Because a stellar surface's brightness is extremely sensitive to temperature, even a small decrease leads to a dramatic drop in emitted light. When vast regions cool at once, the impact multiplies. Betelgeuse was already losing visible light due to the dust cloud blocking some of its emission from Earth's perspective, but the star spots introduced a second independent mechanism of dimming. The star itself was producing less light. The combination of internal dimming from the star spots and external dimming from the dust created the unprecedented drop in brightness that stunned astronomers. One effect revealed the other. Without the star spots, the dust cloud alone might not have caused such a dramatic dip. Without the dust cloud, the star spots would have made Betelgeuse appear cooler and darker, but not enough to trigger worldwide attention. Together, these two factors acted like a perfect storm. The star ejects a massive portion of its surface. This eruption disrupts its convection and forms cooler patches, and the cooling allows the ejected gas to condense into dust right where it can block our line of sight. The star spots deepened the dimming at the same time the dust cloud grew thickest, making Betelgeuse appear weaker and more distorted than ever before. The event became a rare demonstration of how intertwined the internal physics of a dying star is with its external appearance. Betelgeuse's star spots weren't just surface features. They were visual clues to the internal chaos unfolding as the star approaches the final stages of its life. Betelgeuse reminds us that even the most familiar stars can surprise us, and that the cosmos is full of mysteries still waiting to be unraveled.